controller time constant. True. And if it can't be reached, if I wanted a pressure of 18,000, it wouldn't be able to reach it. Because the system can't do what it can't do. I'll say that another way. The system can only do what it can do. You with me on it? Let's do another one with a little bit larger time constant. I mean, what do you call that? Integral time constant. 5 times as large. And I don't need to wait 60 seconds, and I don't need to run that for, I don't know, maybe I do. What do you think? Right on. No big surprise. And the proportional controller, did you notice did you notice that that form didn't ask what the bias was? It didn't ask for the, what do we call it other than bias?
ENGR?
ENGR. You notice the form didn't have ENGR on it?
Awesome.
The proportional controller finds what it wants for ENGR. So the proportional controller, the PI controller, sorry. The PI controller finds this for us. Is that a miracle?
It's unbelievable.
Very sweet.
Unbelievable miracle, isn't it?
Yeah.
At 60 seconds, this is a larger value of calcium integral time goes. What did I change? Oh, I changed the gain. So, one thing I noticed about changing the gain, a bigger kick, and it got up to where I wanted it, at 40 centimeter water faster. What else do you notice? It oscillates more. It's always true, if you increase the gain, it's going to oscillate more. But if you increase the gain, it reacts faster. So here's, in general, what I want you to do is find 2 or 3 good experiments that you did with proportional only. You want me to write these down and put them on the web?
Yeah.
Sure. Let's say 3 experiments you like. Repeat only. Feedback. Repeat them for set point, delta set point, KC, time and all that stuff. Length. Time of change your set point. And passive eye that you get from about So I'll email that to you. Let me show you another thing that can happen with integral. Oh, by the way, look at these. These aren't as simple as what you saw before. Before you saw only one diagonal line and then another diagonal line. The integral controller, hello, who did that?
I think it has a mind of its own.
The integral controller, in essence, keeps moving this thing that we call the controller operating unit. Let me show you another experiment. I can kind of do this. All right, let me change this. I'm going to have the initial set point at 2. On the pressure system, what is the maximum pressure, right? What's the maximum pressure for these valve positions that you can get SSOC? Who has this system with these conditions? You have pressure. What do you have for dampers open and closed?
We got both closed.
Both closed all the time. What is the maximum pressure that you can get from your system?
Our range is 35.
What does that mean?
I can tell you off the top of my head what the maximum output, what the possibilities are. I know our top's 35. I stopped there.
I tell you what, I'll run an experiment. We'll find out what the top is, okay? I'll tell you a secret, you don't have to put in your name and email address and all that. Well, I shouldn't tell you that. All you have to do is put EMCS, that's the secret. We're going to run this for 20 seconds. We're going to have 100% input and always closed. And we're going to see what happens.
That is explain.
Okay, it looks like about 80 centimeters of water pressure is the maximum. Okay, so we'll go back here. And I'm going to go from the initial set point of, let's say 10, and I'm going to go up 65. So 65 and 10 is how much?
75.
It's still in the operating range because it went up to 80, right?
I believe it.
Let's see what happens. Let me see. Controller integral time. Did I do smaller than 2 a while ago? 1?
No,
I never changed it smaller than 2.
no.
I changed integral time, integral controller gain?
Yes,
What was it used to be?
0.2.
I'm going to leave it there and see what happens. Oh, no, I'm going to change the point. Good point. Let's see what happens. notice that it's trying to find M bar. It's trying to automatically find M bar to get the red down to the green. It's getting there, M bar 34, something like that. It's a hidden M bar, self-calculated M bar. All right, so when's it going to change at 60 seconds? So it's getting pretty much, by the way, for all of your experiments, you have to let it run long enough so that this reaches the set point before you change anything. I saw a presentation today that didn't have that situation. Invalid experiment. Doesn't tell you anything if this hasn't reached the steady state before it changes. Okay, I went from a set point of 10 up to 75. And it's reacting. Look, it's getting up there. Sweet. Right? Took about 20 seconds before it got up, get up there, but it got up there. Let me run another one because there's something I want to show you. I'm going to use a smaller integral time like 0.5. Let's see what happens there. This ought to work. This ought to demonstrate exactly what I want it to demonstrate. It's going to demonstrate something called wind up. The integral term on a proportional integral controller can have bad results. Hello. Anybody running a pressure experiment? You just ran one?
Figured you'd be done by the time you get done talking, sorry. Hey man, I own it.
Any questions? Stephanie?
Nope.
Did I answer your question by email?
Yeah.
By the way, a number of you have sent me questions on email, and I said, I'll look into it, or thanks, or good, or whatever. If you sent me an email that says, hey, Dr. Henry, I have a 0 for something or other, I'd send you back an email that says, I'll look into it, or something equivalent to that, right? And I would suggest if you haven't seen that I've looked into it, that you might send that again. What's happening? Oh, okay, look. Did you notice that it got here faster with a smaller integral time constant? Because the integral time constant is in the denominator, and it makes the action happen faster.